All right, so here we are. This is exploit development, and we're down to format string bugs. So I'll talk about them in the lecture, and then I'll demonstrate a few of these things in the projects, although I'm probably not going to get to the format string for a couple of weeks, the explicit demonstration of that. Could we instead screenshot the archive showing we got the flag? Samantha, if you're turning in stuff in the automated scoreboard, don't turn the same project in Canvas. Just one or the other. So let me make this clear because some people are getting confused about it. If you do the projects, you can turn them in Canvas. That's the process described here. And many students like that because they're used to using Canvas. But if you're not addicted to Canvas, you can use the automated scoreboard here. And whatever you turn in here, don't turn it in Canvas at all. We've got your score right here. We can copy your points over. And there'll be a CTF field, and you can just turn in a screenshot of this page and tell us what name you're using if you're using a fake name. If you're using a real name here, we'll find out. We'll find the points easily. The people that are using a fake name like I might be an issue, so make sure you tell us what name you're using. That's all. You don't need to turn things in both places. So I hope that helps. And if you got any confusion, let me know. I'm here Monday through Thursday evening. No more Friday, but Monday, Thursday evening, I'm always here to answer any questions. So let me know if you have any trouble about grading or turning things in or anything like that, or getting your virtual machines running, which is a common thing that people have trouble with. Anyway, we're up to, I think, chapter 4. Right. So let me get my chapter 4 slides up, which are here. All right. Whoops. There we go. Supposedly. All right. Here we go. All right. So we've talked about buffer overflows before, and I'll be demonstrating that project tonight. But I'm trying to make this window a different size. There we go. All right. But now we're going to talk about format string bugs, and you'll see what I've been telling you. If you understand buffer overflows, they're all very much a small variation on that. So format strings. Now the fundamental problem with everything we're doing here is that bytes are bytes. So the same series of bytes could be an integer, a character, an instruction, a string, an image. That's the problem. The computer doesn't really know what those bytes mean, so you can trick it. You can feed in something that it thinks is like a password and get it to interpret it as executable code. Now the format string controls the output. This is a fundamental issue in C. So if I set if I can have this, I invite you to notice what garbage C is. Character A equals 65. So I've defined a character variable A, and then I've set it equal to a number, which, by the way, doesn't make any sense, but this is the way C works. It assumes the only thing we care about is English, so the only thing we care about is ASCII, and characters are just integers. So when I put in 65, that's the ASCII code for a capital A. So I can now print that thing as a character, but I could also print it as an integer, either way. So you see these various format strings, decimal with 5 places, hexadecimal, character, string, and a pointer. And here's some more hexadecimal outputs. You can print lots of things with all different formats. And so the correct way to use printf is to have a format string and then variables to print. But notice, I put something here with format strings but no variables. Now, a more sensible language would just give me an error message and not run. But C just does it. So it just prints random data it found on the stack. And if you understand how this looks in the assembly code, you'll see why. When you call something like printf, what happens in the assembly code is it pushes all the arguments onto the stack, then it jumps into printf. Then printf looks on the stack where those arguments are supposed to be, and it assumes that they're whatever you want there. So it doesn't know that I didn't provide the arguments. It just prints whatever data it found on the stack, which is going to be data that is left over from some previous operation. So this is a data exposure vulnerability already. I'm seeing data that was not intended to be visible by the developer. All right, is ChatGPT allowed in any of these competitions? I think it is. I don't think they can stop it. I know the CCDC competition, the rules are you're allowed to use anything that is public that the other teams have access to as well. So I don't think they care if you use ChatGPT. If you use it to write up the reports you send to the graders, they get mad about that, though. But if you were to use it to figure out how to respond to the attacks, I don't think they would know or care. Anyway, so most important for us, hexadecimal is a way to print out, and you can have a number before it that says how many characters of hexadecimal. And this is going to be important to us in what's coming up next. So, format string vulnerabilities go like this. You would think the format string doesn't really matter that much, but it has problems. So here you see, if I give character name with 10 characters, and then I copy a long name into it, she just does it without complaining, because it doesn't remember that the name was only 10 characters long. It doesn't go back and check. It just calls string copy. All it does is make sure the name points to some address, and then it has a string here, so it copies that string starting at that address. It can do it, so it does it. It does not have any facility to go back and notice the mistake that the string is not long enough. So you can print with no arguments like I just did, and if you do, it will just find the next 4 values from the stack and print them out. All right, so now here is another one. You can, let me pull this one down. Let me get it live, ED204. Let me just bring up project 204 and start it here so I can show you this. All right, so here, that's a Metasploit. I don't care about that, right? I just want to wget. Okay, I'm going to wget these two things. I've got my Intel-based machine here, which is running on my ARM processor, but it's a simulated AMD processor. So, right. All right. Should be letting me in. Yeah, it runs a little bit slow, but that's all right. All right, so CD 127. All right, so I download this stuff. Good, all right, now, and there it is. So now if I do ls, I've got ed204.c, and I have an executable, ed204. So let me make my window fit a little better here and make the font bigger. All right, so let's look at the code for this. Oops, that's the unprintable assembly code. Okay, here's the code for this. So what it does is it takes a command line argument, argc ***augv. If you don't have 2 words in the invocation, which is the name of the program and an argument, it will tell you you need to have a string there. And if you do have a string, it will put that in this variable called buff, which has room for 1024 characters. And then it will just print buff without any format string. So if I run this, and I put in, it's going to tell me I need to put in a string. Okay, so let me put in a string. If I give it AAA, it prints AAA, so that's fine. But what if I give it %x? Then it prints AAA, and then it prints whatever it found on the stack, because I just told it to print the data that came from the user without a format string, so the user could put a format string in there. And that means I can print lots of data. I can put %x, 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 and print lots of data. I can put delineators like dots in here, so I can tell them apart. And now I'll see various 32-bit words of data from the stack. Notice the 25 2E78, that is this stuff in ASCII. And I can tell if I put some A's here, then I will eventually find them. In fact, if I put some A's here, I think I'll find them sooner. Let's try this. There, see the 41, 41, 41? The A's are on the stack somewhere, so I can find the data I put. It's on the stack. So, all right. Let me go to my slides. All right. So that's what's going on. Read 4 words from the stack. Now, the %n format is one of the crazier things in C. Instead of reading data from the stack, you can write to RAM. I have no idea why this exists. You can give it an address, and it will write to that location. I have no idea why they put this feature in the print command. It's insane. It's like designed for hackers. So I can write to a memory location that I arbitrarily define here. And so, of course, if I don't control it, and I just put in %n a few times, it's going to write to random locations on the stack and give me a segmentation fault, of course, because those random locations are probably not valid addresses. So now we're getting there. So all I have to do is I have to choose a RAM location to write to that will give me control of the box. So the question is, can I find a RAM location that will end up in the instruction pointer? And that turns out to be pretty easy to do. If you debug the program, all right, and then you disassemble main, I think, right? Yep. All right, now, if I find the printf command, we'll find where printf is. And what I want to do is I want to just see the system calls. So here it does some stuff getting it ready, like this PC thunk stuff is something having to do with setting up the stack. Then it calls printf. Okay, so here it is printing something. Just look at the right. You don't have to read the assembly code, just read this yellow stuff on the right. These are the system calls. These are the C library calls. So it calls printf. Now, later on, it calls exit, calls string copy, print, put char, and exit again. So what's going on is, I know the source code of the program. In fact, let me put it on the screen next to this, so this will be easier to understand. The source code is here. Okay, so first I have a printf here to warn you that you didn't give me a parameter to start the program like you were supposed to, and then I have an exit. So that's what this is. Print this usage message and exit if the thing was not invoked correctly. So that's what's going on here, printf and exit. Then down here, I do a string copy, a couple of printfs, and then an exit. Here's the string copy. This is where the buffer overflow might happen. I do a string copy, but I'm not going to have a buffer overflow. There is a buffer overflow vulnerability here, by the way, but I would need inputs longer than 1,000 characters to exploit it, and that's not the point here. It does the string copy, then it does the printf here. This is where the actual flaw is. This is where it prints without a format string. Then it has put character, you just put the carriage return at the end, and then it calls exit. So what this means is, at this point, at this printf, I have an opportunity by putting in a %n to write to memory. Now what I can do is I can write to the memory locations that control these C library calls. So I can overwrite one of them and change one of these C library calls to do something different than it should. So I can choose either of these to write to, put char or exit. If I overwrite the address of exit, then down here when it calls exit, it will go into my control. I could just as well do put char, but I think what I did here is I did it with exit. So now we have to control a parameter. And you'll see if you put text on the stack, here, let me get out of here. There. So as I said, if you put 4 characters here, that appears on the stack as the 4th thing on the stack. Here I am printing out the 1st, 2nd, 3rd, and 4th word on the stack. 1, 2, 3, 4. So whatever I put there is the 4th word on the stack. There's something else in the way. So now I know how to control an address there. So if I do, I can put an address there in the first 4 bytes, and if I put a %n as the 4th format string, it'll write to that address. So now, if I want to find a location to write to, I'm going to write to exit, and here's where we can talk about the structure of the operating system. The procedure link table and the global offset table work together, because think about this. You have a program, and you compile it, and then you use the compiled code. Now, what if you update the operating system underneath it, and the address of some of these system calls changes? There has to be a table of offsets in the operating system pointing to where these things are, which will be updated, so that when your program calls where printf is, and printf has moved, it will call a table, which will then send it to the new printf. So you need a indirect address on that end to allow updates of the system. Now suppose anyway, there's also one on the other side. I think if you recompile it, so there's 2 things it uses, a procedure linkage table and a global offset table to hold the current addresses, and you can see them with obj dump. So if I do obj dump and look for the relocation records of the program, it'll show me the relocation records used by this program, and you can see I use printf, string copy, and exit. So the one I care about is exit, and the address of exit is stored at this address, 0804A014. So that is the address to write to if I want to take over the box. If I change that address, then when it tries to call the system, the C library call exit, it will in fact go to whatever address I fed in there. So I can do that here with GDB. So let me run it again, GDB minus Q. We can see this work, ED204. All right, now I'm going to examine that location with this command. I'm going to examine the contents of the address of exit and see, here's the address, and it tells me that's the real address of exit. Now if I run the program with this data right here, this is going to write 4 bytes, 0804A014, to that address. It's going to write something else to that address because I didn't have %x, 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 %n. And I found out before, the first 4 bytes I put in as a string are in the 4th location on the stack. So it's going to print out 3 bytes of data, and then it's going to write something to that address. So when I do that, now it's going to change it, and now the program's going to crash. And the reason it crashed is because that address that used to point to exit now contains the address 1B, which is an invalid address. So I have now created a DOS attack. I put in some data that causes the program to crash. Now I just have to figure out how to control this address and make it point to something useful. Now, what did it write there? It turns out, for some ungodly reason, what the %n thing does is it prints out the count of characters that have been printed so far by printf to a memory location. I don't know why this exists, but that's the way it is. So you can write a Python script that will do this 4 bytes at a time. So let me get out of here and make f1.py. All right, and so what you got here is it's going to write 4 bytes, 14, 15, 16, 17. And remember, the address we wanted ended in 14. So it's going to write 4 times. It's going to write this one and that one and that one and that one. It's going to create a string that includes those things in that order. And so that's going to write 4 bytes to it. Let's try that. And so if I go into the debugger, first let me make this executable. All right. And so now if I run that F1, you see it prints out junk, 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 junk. Then it prints out %x, %x, %n, and n, and n. All right, and there's some unprintable stuff you can't see there. But anyway, let's start the debugger, GDB, minus Q of ED204, and then do this run, which will run it on the output of f1.py. And now, there's the address, 37 3F, 4F, 47 4F. You can see it there. You can also examine it explicitly with this X command. And you can see what happened. I got to have the X there. All right. That's what was written here. And the point is, it's writing, each time it writes with %n, the value it writes is equal to the number of characters printed so far. So that was 37, and then the 3F, and then 47 and 4F, then the count keeps going up. So now I can write numbers here, and I can control what number is written there by making the number of characters equal to the value I want to put there. So I can target a specific value, and here's the code that does that. This is F2. What you have to do is write a large number of characters exceeding 255, so it wraps around. So this is f2.py. All right, and so what it's doing here is, see, the first one is 256 plus this, the next one 256 times 2, 256 times 3, 256 times 4, because each time it's going to write 4 bytes, but I'm only caring about the lowest order byte. And I'm going to write 4 times. I'm going to write to the address here, ending in 14, and then again, and that's going to write something to 15, 16, and 17, but I don't care about that, because on the next write, I'm going to write to 15, 16, 17, and 18. Next time, it's going to write to this in 4 bytes. So I'm going to, with 4 write operations, each adding 256 times integer plus the number I want, I'm going to be able to change these 4 bytes to be whatever I want, and I'm going to do some collateral damage 3 bytes off the end of this, which I don't care about. So now I can write arbitrary stuff there, and what I'm going to try to write is AA, BB, CC, DD, just to prove I'm in control of the pointer here. All right, so let's try this, and what you often find is you have to adjust it on your system. So let's chmod f2.py, now gdb, all right, and now run with F2 and see what goes in there. I was hoping to see AA, BB, CC, DD, and what I got was B1, C2, D3, E4. All right, and all right, so it didn't happen here, and that's what I warned you. This will happen. It depends on your system. So I wanted this to be AA, but it's really B1, which means it's A, B, C, D, E, F, 0, 1. It's off by 7 bytes. Now, if you're smart, you could figure out why, but I'm doing it's off by 7. I think I want it to be 7 less. Notice this subtraction variable here, 29. I think I need to change that to 22 for this system. And exactly how many you need depends on your system. But I'm moving it by 7, and if I figured it out correctly, this will fix the problem. If not, I'll have to try again. I highly encourage trial and error for these things. It's too much bother to think too much about it. I run it. Okay, now I'm getting B, I went the wrong way. Now it's B8, C9, so it got worse instead of better. I was looking for AA, so I wanted to add instead of subtract there. So let's quit, and I know why, because that was a subtracted quantity, not an added quantity. It was 29, so I want it to be 36. To move it 7 the other way. I want to print less characters because the numbers are too big. And you just have to adjust this to match your system. All right, let's see if that did it. A4, B5, well, I'm having more trouble than usual, all right? So A4, I want it to be up by 6, all right? Let's try it again, all right? A4, all right, that was A4. I'm going to just change this by 3 because I wonder what's going on here. All right, it was A4. Now it's A7. Okay, I'm getting there. So 3 more should do it. 36. All right. I think 36 will do it. Or maybe I needed to go to 30. I don't remember how I was adding or subtracting here. We're going to see. Yep, must have had to go the other way. All right. Must be 30. All right, let's try that. There we go. Now I finally get AA, BB, CC, DD. So I just had to adjust that parameter as needed. Somebody else figured it out. Good, somebody ahead of me, they figured out it was 30. Good, anyway, that's fine. You can figure it out if you're smart. I just use trial and error. Too much bother to be smart. So anyway, all right, so now I've got that under control. Now I can hit. Now, we're going to make shellcode, which I don't think we've done yet in this course, and it's a good thing to see. Let me check my slides and see how I'm on track here. All right, so that's what I wanted to show you. In fact, I think that's probably enough for the demos today. Yeah. Well, all right, might do the rest of this. Let me just carry on while we're at it. All right, so let's finish. It'll be count as a demo of this project. Okay, now we can jump to an address under our control. So we're going to insert shellcode, and what we're going to do, here's dummy shellcode. We're going to have 100 90s. 90 is NOP. And then I'm just going to put in CC times 250. CC is break. So all it's going to do is nothing, 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 break to go back into the debugger. So this won't do anything, but it will be shellcode, and I'm going to add it on the stack after all this stuff. So it's just going to be somewhere on the stack. The point is to see where the shellcode is and make sure I can execute it. So I'm going to save this one. This is F3. So get out of here and nano f3.py. All right, and now remember I got to fix this. Instead of 29, it's got to be 30 on my system, which one of the people in chat figured out, which is cool. Okay, there. Oh, it's because I was doing decimal instead of hex. You're exactly right. That's why I was in trouble. The difference between 29 and 30 is 6, not 1, because it's hex. That's what I got wrong. Anyway, good. I'm glad you folks are on top of it. So I chmod plus x f3. All right, and now I'm going to run it. All right, I'm going to GDB it to see what's going on with the program. ed204, and then run it with F3. All right, and so there it is printing out all this junk. It prints out junk, and then it prints the injections, and then this is the shellcode, my fake shellcode, just unprintable characters like a NOP sled and then break code. So now it's stuffed with AABBCCDD, which is fine. Now I'm going to check the address here in the instruction pointer, and that is what I expected, AABBCCDD. And then I'm going to look at the contents of the stack here. So I look at 100 bytes on the stack, and you see here's what's on the stack. Here's the stuff I injected before to make the format string attack work. And here is the NOP sled, 90, 90, 90, 90. And here's the breaks, CCCC. This is my shellcode. So now I can see where it is. I just need to pick an address that hits the middle of my NOP sled. And this is why you use a NOP sled, because it's easy to be inaccurate at figuring out where you are. So you give yourself some room. So I just pick an address in the middle that doesn't contain any zeros, any null bytes. So there's an address in the middle of my NOP sled. Okay? Make sure you use the correct address for your system. So now I'm going to run dummy shellcode. So I'm going to get out of here. Q, Y, all right. And I'm going to nano f4.py. And I'm going to put in that number I put in my clipboard here. That's my target address. All right, and now I'm going to paste in this code here. And I'll move that target address someplace to, oh, I see, I'm going to go here, there. I'm going to do it in 2 stages because I want my target address to be near where I need it. There, I'm going to need these bytes here to turn into that target address. There. There. So, all right, this is what should be my target address, FFFFD11C. It's FFFFCF9C. This is the ones I have to fix. This should be CF9C. There. That should hit the NOP sled on my system. So, let's try that. So now I run this in the debugger. And, whoa, that's not right. Let me just cancel that. Now I want to run it on F4, okay. And notice it exited normally. It didn't crash. So that's interesting. I expected it to hit a breakpoint, so something went wrong here. Permission denied. Oh, I couldn't execute the code. I forgot to make my code executable. Okay, just got to read your error messages. I got a chmod plus x f4. All right, now I can go back in here and run F4. And now it did a seg fault, so it failed. So something didn't work here. Let's examine what's on the stack. x/100x ESP. Well, there's the 90s. So this FFFFCF9C is good. Let's see if I can figure out why it didn't work. I should be able to examine the offset address, which was here. Something's wrong with the address in there. Maybe I got it backwards or something. there it is. Whoa, totally wrong. All right. Let me examine my Python code and see what question just means unprintable characters. How do we, does the stack address not change because of ASLR? Well, it does, but not in the debugger. The debugger has ASLR turned off by default. How do we ensure the target address is right? Well, that's what we're going to do. I've made a mistake here, and let's see if we can find it. So I nano F4. All right, so the target address is FFFF-CF9C. And I might have that backwards. Let's take a look back here when I was doing AABBCCDD would actually hit at there. AABBCCDD, right to left. Okay, so the first one goes on the right. All right, the first one goes on the right. Yeah, so this looks, but it's little endian. I think these are in the wrong order. I think that's the problem. No, I'm not so sure of that. All right, let's go back to this. Let's go back to AABBCCDD and see if that's going to work. Here's the code that does that. I'm just going to put it in after this code and see if I can understand what happened here. All right. Let's get back into the debugger and then run f4.py. All right. And now it has 1BC2D3E4 instead of AA. My thing, I'm off by 6 again. All right, that's my problem. So I got to fix that. Let's get out of here. I forgot, somehow my correction for that 6 was wrong. And oh yeah, I got the 20, I don't have the 30 in here, that's why. Okay, this had to be 30, we've already figured that out. The code here was for a different system when I developed this project, and you have to customize it for your system. There, let's try this. Now it should give me AABBCCDD, which is good because I can tell what it, I run f4.py. Yeah, now I get AABBCCDD. Okay, good. So now I'm in control. Now all I have to do is get rid of these statements here. I'll comment them out. And now it should go to that address, which is the real address of my NOP sled and shellcode. Now I get the breakpoint trap. That's what I wanted to see. Now notice I ended up here at FFFFCFD5, and if I examine the stack, then I ended up at CFD5, which is here. Just exactly what should have happened. I hit somewhere in the NOP sled, and I executed NOP, 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 and it stopped as soon as it hit the first CC. So this proves I am able to execute code here because it went through the NOPs, and it ran through them and it hit the CC. So now all I have to do is put whatever I want to happen down here. That's what you call the egg. So that's good. All right, so it's working. All right, now all I have to do is make real shellcode. All right, and for that, we're going to use Metasploit, which we've done before. Or I don't think we've done it yet in this class, so it's time to do it. There, that's how you get Metasploit. So first I have to install Metasploit, which I think is up here. Yep, here's how you install Metasploit. This curl command will get the latest Metasploit installer for Linux. So I download the Metasploit installer, and then chmod 755 will make it executable, and then I run it. All right, give it a password. This will put Metasploit on my Linux machine. And then I'm going to use Metasploit to write some shellcode. And that's way down here somewhere. All right. There we are. That's the command. This is going to make a shell bind TCP, which will start listening on port 4444, and it's going to skip these, which are bad characters. I didn't bother going through it in the demo. In project, it shows you how you can show that these characters break it. Since we're just inputting a string, as you would imagine, null byte will terminate it, a carriage return, a line feed, a space, or a tab. All those characters will terminate the string, so you have to tell it to avoid them. And this prepend fork equals true seems to be necessary. There's a few advanced features in Metasploit, and as you may have noticed, I don't think about it too much, I just try them. When my shellcode fails, I try turning on the advanced features until it works. So I found that worked here. So that's the command that will generate shellcode, and looks like it's taken a while to download. So I think I'll quit the live demo. I'll just say the shellcode just gives you Python code. You can copy and paste to put in there. And you just put that in instead of the CCs. Keep the 190s, which is the stop sled. You put in the real shellcode, and then you put in enough padding to keep the total length of this the same, because I talked about that before. Once you have any kind of exploit, always make sure and keep the total length of it the same to make sure you're hitting exactly the same vulnerability, just as a general good practice. And then what will happen is when you run that, it will start a listening shell. And if you run ss-pant, you'll see it listening on port 4444, which is the default for Metasploit shellcode. So that's what I wanted to show you. And all right. And so if you have trouble, another thing I mentioned before, you can also use this encoding it as just alpha characters, which is another way to make sure that your shellcode will not get damaged when being input into the program. Anyway, that's what I wanted to show you for this. And we're just up to 10 minutes to 7. Let's take a break until 7, and then I'll do a couple of slides and the Kahoots and a couple more demos. So let me just stop this recording.